So with a trig equation, it's just an equation that involves one or more trig functions, and usually what we're looking for is the argument inside the function. For example, if I want to solve for theta, where theta is between 0 and 2 pi, and then, theta is the argument inside. I got 2 times cosine theta minus 1 is equal to 0. A couple of things to observe about this right off. They will let us know in the problem itself whether or not they're looking for an angle in degrees or radians. I can tell they want an angle in radians because they specified that theta was between 0 and 2 pi. And if they wanted it in degrees, they'd say where theta is between 0 and 360. Also, these functions are periodic, meaning they repeat themselves. There's probably infinitely many values that will make this equation true. But this says limit ourselves to one go around the circle, which is sort of a standard limitation that we place on ourselves. So the first step, or my first sort of intermediate goal usually, is to say, I know I want what theta is, but maybe in this equation here, I'm going to start out by figuring out what cosine theta is. So I'll treat cosine theta like it's my variable, get that by itself. So we could add 1 to both sides. So we get 2 cosine theta is equal to 1, and then divide both sides by 2. And we get cosine theta equals 1/2. So I'm looking for the angles, just one go around the circle, where cosine theta is equal to 1/2. Now sometimes we might need to rely on the calculator, but a lot of the time we'll be in a position where they've given us some convenient values, and all we need to use is the unit circle. So if I'm looking for a spot where cosine is equal to 1/2, and this is almost a little bit cut off, but can anybody point out some angles where cosine is equal to 1/2? Pi over 3, so that's up here. Because cosine is the x-coordinate, so I'm just scanning the points along the edge of the circle, looking for an x-coordinate equal to 1/2. So there's pi over 3, where else? And 5 pi over 3 down here at the bottom. Let's see, so using the unit circle, we get theta is pi over 3, 5 pi over 3. Those are nice angles, right? Wouldn't you say? Aren't those some nice angles? Pi over 3, 5 pi over 3. If you were using the calculator to solve this, if I know what cosine theta is equal to, what do we need in order to find the angle theta? The inverse cosine, yeah, or the arc cosine. So theta is arc cosine of 1/2. Now I have to realize, and we spent some time working with this before, but arc cosine will always give you an angle between 0 and 0 and pi, right? So it's on the top half of the circle. So when I do this, it'll give me one of the angles I'm looking for. Let's see. I'm in radian mode, so inverse cosine of 1/2, and I get 1.047. How would I get the other one? So there are two answers to this.
Multiply by 180 divided by pi.
Nope. That's if I wanted to get an answer in degrees, I could do that, but that's still not the two answers, right? There's two. So like the pi over 3 and 5 pi over 3, those were two different angles. Alex? 2 pi minus whatever that is. Yeah, so 2 pi minus 1.047, and that gives us 5.236. Now, I'd say that these are equally acceptable answers, but I want to caution you against relying too heavily on the calculator when sometimes the unit circle will do. First of all, These are some nice looking angles, aren't they? Right? They're exact. I didn't have to round this at all, right? Also, sort of conceptually, we can find these angles, right? I know, and even if you do use the calculator, I want us to start thinking, having our minds going to the unit circle. Just if only because I know that if I'm looking for where the cosine is a half, that's a positive a half, and I first have to identify, I know I'm going to expect to get a result in quadrants 1 and in quadrant 4, right? So the reason to get the other angle, we did 2 pi minus, is because we knew, right? Alex knew at the start that we were going to get an angle in quadrant 4, and so when I found this angle, that's like the reference angle that we were looking for. Okay. Let's try another one. This one is arguably a little bit more involved. And the first thing that stands out to me when I look at this equation is that it has two whole functions, there's a cosine squared and then a sine. The fact that one of them is squared is interesting in itself, but the fact that I've got two different functions makes this a little bit more difficult. So I really want to be able to try to write this in terms of one function. And lucky for us, we have a nice Pythagorean identity that'll do it for us. We can use Pythagoras to help us rewrite cosine squared x. If we, what does Pythagoras tell us? Okay, yeah, so we know that sine squared x plus cosine squared x is 1. So we can use this to rewrite the cosine squared. That means cosine squared x is 1 minus sine squared x. That's Pythagoras. So let's substitute. Now we have just one function. That's a lot better than we were before. Let's simplify this a little bit. We get 2 minus 2 sine squared x minus sine x minus 1. And combining like terms, we have minus 2 sine squared x minus sine x plus 1 equals 0 because I have the 2 minus 1. How's that so far? I'm going to do one more thing before we launch into solving it. And the reason, so the thing I'm going to do is I'm going to lead off with a positive sine squared, so I'm just going to multiply through by negative 1. But the reason I'm doing that is I look at this and I say, that's a quadratic equation. It's just quadratic in sine squared. You know, solving this will be just like solving minus 2x squared minus x plus 1. If I see it as a quadratic in sine, that's what I can use to figure out what sine x has to be equal to. And once I know what sine x is, I can go to the unit circle or use inverse functions to get the argument. So I'm going to multiply through by minus 1. So we get 2 sine squared, whoops, I'm leaving off letters. 2 sine squared x plus sine x minus 1 equals 0. Now if I have a quadratic that's set equal to 0, what is one of our favorite ways to solve? We have two favorite ways. Factoring. That's often my first go-to, right? Because if it will factor, that's usually a little easier than completing the square, a little bit less labor intensive. We could complete the square, but I think we could try to factor. So if we unfoil this, my first two terms have to multiply out to 2 sine squared. So what are they going to be? What do we need? 2 sine x and sine, yeah. So 2 sine x and sine x, like minus 1 like here, and then plus 1, and then just doing a quick check, there's a plus 2 sine x, this is a minus sine x, And these do combine to give me a positive sine x. I'm going to pause there for a moment and just see if we're okay with this. Because that recognition that we could treat this like any other quadratic equation is probably not obvious. It takes a little bit of practice. But it's also not rare that it happens. So we're going to be on the lookout for that when we're solving equations. So we have it solved. We don't have it solved. We have it factored. What's left before we get it solved? Yeah. So right, that's why we factor. That's why factoring by solving works. So that's the mechanism by which it works. Is a product is only 0 when one of its factors is. So we know that 2 sine x minus 1 equals 0, or sine x plus 1 equals 0. And now each one of these two equations, very similar to the one we just solved in the example above. So we can, on the left side here, add 1 to both sides. So we get 2 sine x equals 1, and then divide by 2. We get sine x equals a half. On the other side, all we do is subtract 1, and we get sine x, equals negative 1. Now we're very, very close. Sine x equals a half. Working with this side here, let's use our unit circle. Where is sine equal to a half? What are we looking for?
6.
Pi over 6, yep.
5 pi over 6.
And 5 pi over 6, because we're looking for where the y coordinate is a half, so that happens here, and then reflected across on this side over on the at 5 pi over 6. So we have pi over 6, 5 pi over 6. And what about, where's sine x equal to negative 1? 3 pi over 2. The y coordinate, I realize it kind of is cut off, but the y coordinate is negative 1. That's at the very bottom of the circle. So there are 3 solutions to that equation. Questions? Okay. So this one was interesting because it was an equation that first had 2 different functions in it, and we had to work to try to first write it in terms of one function, right, and then isolate that function. This next problem has just the one function, just the cosine. But what is it that makes this one interesting? It's not just that I have x over 2, it's that one of them is x over 2, and what's the other one?
1 plus.
Nope. I've got x over 2 in one of these cosines,
Cosine x.
and just x in the other one. What makes this one interesting is that these arguments are different. That's something we have to fix too before we can proceed. If I got 2 different functions, I got to fix that somehow, right? So I can make an equation about just one function. But also if the arguments are inside are different, I got to fix that too. So we have some identities to help us out with this. In fact, we have the half angle identity for cosine that will allow us to write this in terms of something that just involves the cosine x. So if we use that, cosine of x over 2 is plus or minus the square root of 1 plus cosine x over 2. Now we have fixed the problem where we have two different arguments inside the trig function. One function, one argument. That's good. But we got this equation with radicals. How do we solve an equation with radicals? Yeah, right. So, and we'll note that it's already set up so that the radical is isolated, right? It's by itself. So we are at the point where we could just square right now. And squaring both sides will be nice because when we square the plus minus, first of all, it gets rid of that plus minus ambiguity. But we're just going to have to keep in mind that when we solve an equation with radicals, we have to check our results, right? Like we saw back, I don't know how many, couple chapters ago or something, that whenever we solved an equation with radicals, sometimes we could get these extraneous roots. So we just have to be aware of that here and check our results at the end. But on the left side, we have 1 plus cosine x over 2 equals, what do we get on the right side?
Plus 2 cosine x plus cosine x squared.
Yeah. So 1 plus 2 cosine x plus cosine squared, and we get that because, of course, we have to FOIL that out on the right side, right? We can't distribute an exponent over addition. We got to FOIL that out. Now we have an equation with fractions, but that we already know how to deal with. But let's multiply both sides by 2. And now we have 1 plus cosine x equals 2 cosine squared x plus 4 cosine x plus 2. I reversed the order because I like starting with, I like writing my terms in descending order. What kind of equation are we looking at? What's that? Yeah, it's another quadratic. Let's set it equal to 0 and see if it's something we can't factor. So we could subtract 1 and subtract cosine x. And we get 0 equals 2 cosine squared x plus 3 cosine x plus 1. Now let's see if we can't unfoil this.
Two cosine x plus 1 times cosine x plus 1.
So we have the 2 cosine squared, the plus 1, and then this is plus 2 cosine x. This is plus cosine x. And those do combine to give me a plus 3 cosine x. Nice. So let's solve. We're going to set each of these factors equal to 0. 2 cosine x plus 1 equals 0. Or cosine x plus 1 equals 0. Solving each of these for the cosine function, we get 2 cosine x equals negative 1. Dividing by 2 gets us cosine x equals negative a half. Where is cosine equal to negative a half? Yep.
Oh, sorry. Cosine, not sine.
So what's the other one? 4 pi over 3. Yep. So just sort of reflected, right, flipped across the x-axis. So 2 pi over 3 and 4 pi over 3. And then the other one, cosine x plus 1 is equal to 0, so that means cosine x is equal to -1, which means what is x equal to? Say that again? Yep. So cosine is pi. Oh, we're not done this problem, you guys. What's left to do? We found 3 answers. We have to check it because when we used that half-angle identity, we said we turned it into an equation with radicals, right? And we know that when we solve an equation with radicals, that can introduce extraneous roots. We actually have to check and make sure, you know, I'm not ready to circle any of these yet until I know that they check out in the equation. So let's see. Our original equation looks like this. Cosine x over 2 equals 1 plus cosine x. So when x is pi over, 2 pi over 3. We had 2 pi over 3 and 4 pi over 3. So when x is 2 pi over 3, then x over 2, half of that is pi over 3, right? And I'm checking to find x over 2 because x over 2 is actually what I have to plug in to cosine on the left side. So plugging these in gives us cosine pi over 3. I want to know, is this equal to, a little question mark there, 1 plus cosine of 2 pi over 3. Cosine of pi over 3 is a half. Is this equal to 1 plus cosine of 2 pi over 3? Cosine 2 pi over 3 is negative a half. Is that true? Pretty sure 1/2 is equal to a half. So that means 2 pi over 3 checks out. Let's try 4 pi over 3. If x is 4 pi over 3, then x over 2 is 2 pi over 3. And so we want to know, is cosine 2 pi over 3, is this equal to, put a question mark there, 1 plus cosine of 4 pi over 3. What's cosine of 2 pi over 3? Negative a half. And what is cosine of 4 pi over 3? Negative 1/2, yep. So is negative 1/2 equal to 1 plus negative a half? No. Negative 1/2 is in fact not equal to positive a half. So 4 pi over 3 does not check out. And one more to check was pi. So when x is pi, x over 2 is pi over 2. And so the equation we want to check, oops, I'm running out of space here, is cosine pi over 2. Is this equal to 1 plus cosine of pi? What's cosine pi over 2? Zero. It's at the top of the circle, right? The x-coordinate is 0 there, although it's a little obscured by the sorry, by the projector screen thing. And cosine of pi is negative 1. So 0, is this equal to 1 plus negative 1? Yeah, that checks. So pi and 2 pi over 3 check out, but not 4 pi over 3. So I'm going to go back up here and be sure to indicate that those are my 2 answers, but not 4 pi over 3. questions? Okay. All right, we got, oh yeah, so we got this one more. So we want to show that, or sorry, we're not showing that, we are solving this equation. We're trying to find the angles that make this equation true. Tan 2 theta minus cotan 2 theta equals 0. So what is the thing that makes this problem maybe a little interesting?
You have 2 theta, and you also have tangent cotangent.
Yeah, so I got two different functions. Now, the fact that it's 2 theta is also interesting. We're going to have to take that into account. But I'm feeling pretty good about the fact that it's 2 theta in both functions. But here's the fact that I've got a 2 theta there. That's going to affect my answers, because if theta ranges from 0 to 2 pi, I'm just going to keep in mind this means that 2 theta is going to range from 0 to 4 pi. And that might be important as we consider solutions later on. So we got two functions in here, but they're pretty closely related. I mean, cotan is just the reciprocal of tangent. So we could write this as tan 2 theta minus 1 over tan 2 theta equals 0. Now this is just an equation with fractions, but we know how to solve equations with fractions. We can turn it into an equation with no fractions if we just multiply through by the LCD, which in this case is just tangent of 2 theta. Now when we multiply through by tan of 2 theta, that we're obviously going to distribute, what do we get on the left side?
Tan squared 2 theta. 2 theta.
Yeah, tan squared 2 theta minus 1. On the right side, we still just get 0. And this is something we can factor because tan squared minus 1 is a difference of squares, so we know how to factor that. So this will look like tan 2 theta plus 1 times tan 2 theta minus 1. And now, again, we have a product that's equal to 0, and we can, and then we can just set each factor equal to 0. So this means that tan 2 theta plus 1 equals 0, or tan 2 theta minus 1 equals 0. This means that tangent of 2 theta is either a negative 1 or a positive 1. Now you could use your calculator here if you like. 1 is a particularly convenient value for tangent, because remember that tangent is sine over cosine, right? So if sine divided by cosine is equal to 1, that means that sine and cosine have to equal the same value. So if we actually think about this one first, where tan 2 theta is equal to 1, that means that 2 theta has to be an angle where sine and cosine take on the same value. So that happens here at pi over 4 and across at 5 pi over 4. And that's the value for 2 theta. When we think about solving the other one, tan 2 theta is equal to negative 1. That means that sine and cosine will have like the same values but just different signs. One will be plus and one will be minus. So going to the unit circle, that happens here at 3 pi over 4 and down here at 7 pi over 4. Now here's where we have to consider the fact that we're solving for 2 theta and not theta. While theta is allowed to go 1 full go around the circle, 2 theta is going to have to make 2 full revolutions. We've only allowed it to make 1 full revolution. So the way that we get the other angles is we just take each one of these that we found and add 2 pi. So 3 pi over 4 plus 8 pi over 4 is 11 pi over 4. 7 pi over 4 plus 8 pi over 4 is 15 pi over 4. Pi over 4 plus 8 pi over 4 is 9 pi over 4. And 5 pi over 4 plus 8 pi over 4 is 13 pi over 4. These are 1, 2, 3, 4, 5, 6, 8 values for 2 theta. And now we are so close to being done. We know what the values are for 2 theta. How do we get the values for theta?
Divided by 2.
Just divide it by 2, right? Yeah. So I know what twice theta is. We'll just divide by 2. We'll do the same thing down here. And that'll get us our sort of real answers, so to speak. So 3 pi over 4, half that is 3 pi over 8. So you can cut fractions in half by doing one of 2 things. You can either cut the numerator in half, which I do if it's even, because it's easy to do, or you can double the denominator. All of our numerators are odd, so I'm just going to double. Whoops, I wrote 3 pi over 2. Anybody catch that? I'm going to double the denominator. We get 3 pi over 8. 7 pi over 8, pi over 8, and 5 pi over 8. And then down here we have 11 pi over 8, 15 pi over 8, 9 pi over 8, and 13 pi over 8. Huzzah.
Rachel, how come we don't have to check for that one?
Oh, we certainly can. The reason that we don't like have to is because, the reason we had to in this example is because after we used the identity, we solved an equation with radicals. Anytime you are solving an equation with radicals, you put yourself at risk of finding extraneous roots, and that is, and this was not an equation with radicals. We didn't have to use an identity that did that.